Good morning, everyone. Like you said, this is my first time in India. I'm really happy to be here. It's a little awkward when you're invited to give a talk. You know, if you submit a proposal, you go in, you say, this is what I'm going to talk about. Well, if they accept it, then you know that they want to hear about it, right? But when you're invited, they usually say something along the lines of, I'm sure the attendees would like to hear whatever interesting topic that you'd like to talk about, which is a pretty dangerous thing to tell me. Heck, the last talk that I gave was 35 minutes of me talking about a video game, specifically a video game called Destiny, which I love. And when I say I talked about a video game, understand me, I mean, I went all in. I was like, exciting gameplay breakdowns showing how to zero in on information in a heads-up display and promptly use that information to make the absolute worst decision that can get you killed so embarrassingly that even the enemy team members spend time kind of pondering what you were thinking. I want you to appreciate the risk that the organizers took to put me in front of you today. Also, I did notice we don't have audio, and I'm going to need audio for my presentation. So today, we're going to talk about video games. Actually, that's a lie. But while we're on the topic, let's talk about lies. As software developers, we're kind of in the business of lying. Steven Spielberg, back in the 80s, he produced a great movie called The Money Pit. And it starred Tom Hanks and Shelley Long. And I almost always end up referencing this movie every time that I talk to someone about an estimate. They had this recurring joke in the movie that no matter who you ask or how big the job is or when you ask them, the estimate is always 2 weeks. I want to show you a couple of clips, and hopefully the audio's going.
How long do you think it'll ever take? 2 weeks. Really? That's all. Who do you think it's got? Just as soon as you check, please. Well, can you at least hang the door? I have cash for that.
So this guy's desperate. He just wants to get some forward momentum going on his project. And he's like, I'll pay you cash right now. Just do something. Here's one more. This time, the contractor has just ripped up the client's house on the first day on the job. And you can see the debris everywhere in the background, and the walls are all ripped up. And he hit a snag due to missing paperwork.
When I do get the permit, how long will the job take? 2 weeks. 2 weeks? 2 weeks? You sound like a parrot. 2 weeks? 2 weeks? 2 weeks?
He doesn't even pretend he's telling the truth. So I should stop here and say that there has to be intent. I realize there has to be intent for a lie to be a lie. And you might say, well, wait a minute. You know, when I estimate, I'm making every effort to give the best, most accurate answer I can. I'm not deliberately deceiving anyone. But let's look at the best case scenario for a second. Maybe you pick some work off a queue and you start working on it, and someone comes along once you've gotten into the thick of things and they ask, you know, how long do you think it's going to take? Well, you might have some idea at this point how long it's going to take because you've started to work on it, but you can't really say for sure. And more often than not, someone's asking you that question before you've even started to dig into the work. And so you basically make something up. You might even pad things a little bit because you know someone is going to hold you to that commitment, and you want to make sure you meet it. So maybe you're saying, I don't do things that way. Not in my shop. We're agile. We're enlightened. We know better than to give estimates using time. We use points. Get it? Points. Yeah, I'm here all morning. So the idea with points is that you don't estimate how long it's going to take, but how difficult it's going to be in relation to something else. Right, and everyone agrees to pretend that you're not really thinking about how long it's going to take you whenever you agree on a point value. Now, when you estimate, you're not intentionally lying on how long it's going to take or how hard it's going to be. The lie is more self-directed. You're lying to yourself. You're telling yourself that you're going to be able to accurately predict when you're going to finish the work. You're telling yourself that you can predict the future. And you can't. We're going to come back to this one in a bit, but right now I want to move on to something else. Here's another area that we tend to be, shall we say, flexible with the truth. And what is Git anyway? You might say it's a distributed version control system. You'd be right, but what is a distributed version control system, or any version control system, really? Well, it's a tool that's primarily concerned with keeping track of history, as in a record of the stuff that's happened, the immutable record of all that has happened so far in your project, right? So if you're setting out to change the past, you're going to fall into one of two categories. Another movie from the 80s. I'm an 80s kid. What are you going to do? Maybe you're Marty McFly. Stuff somehow got all screwed up, and you're the good guy, and you're just trying to set things right in the past to ensure the correct version of the present. Or maybe you're the original Terminator, subservient to the will of the machines, working to ensure their rise and humanity's doom. Whatever you're doing, whether you're doing it by chance or choice or because of your programming, is irrelevant. Now, from the point of view of an altered timeline, it's impossible to know that history was changed, let alone whether that change was for the better or for the worse. That information is lost forever to history. Maybe you think that analogy is unfair. All right, let's look at it another way. Do you know how Git's implemented? It uses a hash tree, sometimes called a Merkle tree. Do you know what Merkle trees are for? For starters, they're for verification of data that's shared between multiple computers. But more specifically, they're to ensure that nobody is lying. I can't make this stuff up. It's literally in the Wikipedia definition. Other peers do not lie. So what's the first thing we do with this amazing tool that ensures we don't lie? We lie to it. And we lie to it a lot. We're running interactive ads so we can put in just little chunks of files, and we're running fix-up commits, and we're rebasing and squashing other commits into existing commits. We're doing interactive rebasing and moving the order of commits around, and we're amending our commit logs. Git's a really powerful tool, and I understand that there are a ton of workflows that can absolutely work well. And there are situations in which these commands are reasonable and maybe even advisable. People usually tell me they abuse these tools and it's justified because they want their commit logs to tell a story. I agree. I'm a really big fan of commit logs that tell a story. It's just that I'd prefer the story be nonfiction. It's valuable to know exactly how things got the way they got, even if those details are sometimes unflattering or confusing at first glance. It's nice to know what was tried and what failed before landing on a working solution. If we can learn from history, we might not repeat it. Look at it this way. Every time you have to force push to a remote, Git's telling you, you're lying to me, and you're saying, I know, but trust me, it's for your own good. You'd better be very sure about that. Maybe we can be forgiven, though, for lying so freely. After all, we're surrounded by lies. Every single abstraction is a lie, if it's an abstraction at all. It's a deliberate attempt to represent something in a way that is more pleasant to work with or think about, rather than how things are really underneath. And as an industry, we've built an impressive tower of abstractions, a tower of lies. And we do our work atop this tower every day. And every story in this tower is one that someone thought was a lie worth telling, for our own good, based on their opinions. Well, as you might guess, I have opinions about some of those lies. Actually, scratch that. I have feelings about some of those lies. So I should probably warn you right now that I'm going to express some feelings you may disagree with. I have feelings about Haml. I have feelings about SAS. I have feelings about CoffeeScript. And I especially have a lot of feelings about Active Record. And feelings are hard. So since feelings are hard, let's talk about something a little easier than feelings. Let's talk about some science. Specifically, let's talk about quantum mechanics. Does anyone here know what this is? Put your hand up if so. Yeah, Mike, I know you know what it is. All right. For those of us who, like me, don't immediately recognize this formula on sight, let's start with something simpler. Does anyone know what this is? This is a pebble. Some might call it a very small rock. And when you drop it in a still body of water, you'll see it produces little waves or ripples. If you drop two pebbles next to each other, you're going to get two sets of waves, and the ripples are going to make a kind of a pattern where they intersect. This is Christian Huygens. Way back in 1678, he was telling people that he believed light was a wave. And he published this idea years later in 1690 in his treatise on light. But a wave needed to be in something or on something, like the waves we see in water. So light was a wave in what exactly? He called this hypothetical substance the luminiferous ether. And I think that just sounds awesome. I wish luminiferous ether was a thing. The problem for Huygens was this guy. Maybe you've heard of him. He's kind of a big deal. Isaac Newton also wrote a treatise on light in which he put forward the idea of a corpuscular model of light. He believed light was a particle, is what that means. And since Isaac Newton said he was wrong, nobody paid much attention to Huygens' theories. There were some scientists, though, who thought Newton was wrong. And in 1801 and 1803, Thomas Young delivered a series of lectures to the Royal Society. He was outlining a wave theory of light, and he added to it a new fundamental concept, the so-called principle of interference. This is a sketch that Young drew based on observations of water ripples. It showed how ripples from one source allowed to pass through two openings in a wall. This is marked A and B here. They created those same patterns that we saw earlier when you drop pebbles in the water. Now, these patterns are called interference patterns, where two waves intersect, and they're both in an up or a down position. They reinforce one another by producing constructive interference. They increase the wave's height or the wave's depth. If they intersect where they're in opposing directions, then they produce destructive interference. They flatten out the wave. Now, along the observation points marked on the far wall, C, D, E, and F, you'd see this reflected in a sort of undulating pattern. If light was a wave, then we could expect that we might see something similar if we observed the pattern created by light shining through two holes. And in 1803, Young performed this experiment, now known as a double slit experiment with light, and as expected, he got the results, an interference pattern. And one of the great things about this experiment was how simple it was to reproduce. However, it was also the bad thing, because even a century after their origin, Newton's particle theories had so much prestige that Young's findings didn't draw much interest, and some even ridiculed him. And in part, that suffering was because he was so busy producing real-world results, real-world experiments, that he didn't spend enough time illustrating his theory with mathematical proofs, and so people didn't take him seriously. Still, by 1817, experiments that corroborated Young's theory had gained critical mass, and Newton's particle theory of light was vanquished for the time being. Classical wave theory went on to allow the creation of things like radio and radar, among others, but it still failed to explain certain other things. For instance, the ozone layer protects us from the dangerous short wavelength ultraviolet part of the sun's radiation spectrum. But when a wave passes into and out of a medium, its frequency is unchanged. Its wavelength is altered while it's in the medium, while it would be in the ozone layer, but it returns to its original value when the wave reemerges. So if light was just a wave, then after it passed through the ozone layer, it would return to its short wavelength, and well, let's just say nobody would ever have to work on their suntan because we wouldn't exist. We need another piece of the puzzle. Let's take a step back to a couple of millennia ago. This cheery guy is Democritus, sometimes known as the laughing philosopher. He is credited, sometimes along with his teacher Lysippus, with first developing the philosophical theory of atomism in the 5th century BC, over 2 millennia ago. He proposed that the universe was made up of tiny, indivisible, indestructible particles he called atoms. This is from the Greek word atomos, which means indivisible. Now, philosophical atoms supposedly came in an infinite variety of shapes and sizes and could be combined in different ways to create everything that we see, everything that exists. Now, this idea survived for millennia, so when chemists and natural philosophers in the 19th century found evidence of tiny particles that seemed to be indivisible, they called them atoms. It was an obvious choice for the name. But it turns out that atoms don't come in infinite varieties, at least not so far as we've found. In fact, there are few enough that it was straightforward to maintain a table of the kinds of atoms we know about. We call it the periodic table of the elements. The other difference between atoms and their original philosophical counterpart is that it turns out that atoms are not indivisible. They're made up of even smaller parts. In 1897, a physicist at Cambridge University was conducting experiments with a cathode ray tube. His name was J.J. Thomson. Now, during the course of these experiments, he discovered that cathode rays were streams of negatively charged particles that were about 1,000 times smaller than a single atom of hydrogen. In other words, he discovered what we now know as the electron. And he went on to theorize that atoms were divisible, in fact, and that electrons were the building blocks of the atom. We call tiny particles like the electron elementary particles. And the electron was the first elementary particle we discovered, but it wouldn't be the last. This is all well and good and kind of interesting, I think. I mean, to me at least, it's kind of interesting. But how does it relate to our discussion about the true nature of light? Well, in 1900, a theoretical physicist named Max Planck suggested that radiation is quantized, meaning it comes in discrete amounts. You can have 1 or 2 quanta of radiation, but not 1.5. Now, most scientists at the time didn't take him seriously, but this guy did. And in 1905, Albert Einstein, who was one of the few scientists who did take it seriously, suggested that electromagnetic waves, of which light was one, could only exist as discrete physical wave packets. He called one such wave packet the light quantum. Now, Einstein carefully avoided calling these wave packets particles, but still, I bet Isaac Newton would have felt pretty smug if he'd still been around. Now, the existence of these light quantums, which would later come to call photons, wouldn't be confirmed until 17 years later, in 1922. That's when a physicist named Arthur Compton performed an experiment proving the quantum nature of X-rays by scattering them with electrons. It stood to reason that if something that was known to be an elementary particle already, an electron, could collide with X-rays and cause them to scatter, then they must be elementary particles as well. But wait, we already established that light behaves like a wave, so which is it? I told you we were going to talk about quantum mechanics. So when we shine a light through 2 slits, we see the interference pattern we'd expect if light's a wave. But if light's a particle, and we know it is, thanks to Einstein and Compton, then we'd also be able to send just a single photon through those holes, or an electron, or really any elementary particle. This is what's called a photomultiplier tube. It is so sensitive that it can detect the impact of a single photon. Now, if we put it in an extremely dark place, and we shine an extremely faint light through those same 2 slits, we can use a frequency counter to tune things until we know it's only receiving a single photon at a time. And then we can check, and we can see where those photons impacted. Now, as the photons are fired through those slits, they appear to be a random distribution at first. But if you track them over a long enough time, something truly amazing happens. Even though the photons are arriving one at a time, the same interference pattern appears. How's that even possible? What's the photon interfering with or being interfered with? The answer lies in something called wave functions, and these are at the heart of quantum dynamics. A wave function tells us the probability that a particle will be observed in a given location. What are these waves of or waves in? We don't really know. Werner Heisenberg and Niels Bohr were physicists who pioneered quantum mechanics at the University of Copenhagen in the 1920s. The interpretation of quantum dynamics that they are largely responsible for is called the Copenhagen interpretation. And the Copenhagen interpretation says that the wave function doesn't even have a physical nature. Instead, it's comprised of pure possibility. It suggests that the particle that is traversing the double slit experiment exists only as a wave of possible locations that ultimately encompasses all possible paths. It's only when the particle is actually detected that its location and the path that it took to get there is actually decided. We call this feature wave function collapse. Now, prior to the collapse, it's meaningless to try to define the particle's properties. It's as though the universe is allowing all of the possibilities to exist simultaneously, We call this particle state a superposition. And it holds off on choosing until the very last instant when we measure it. Not only that, but those different possible paths, those different possible realities interact with one another in such a way that if one particle impacts in one place, it is going to increase the chance that some paths in the future are going to become real and decrease the chance of some other paths. That interaction of possible realities is seen in the interference pattern. And that pattern is real, even if the vast majority of paths that are involved in producing it never attain reality. In the Copenhagen interpretation, the final choice of the experiments of the universe is random within the constraints of the wave function. The theory of quantum mechanics produces accurate depictions and predictions of reality, and it's consistent with the Copenhagen interpretation, but there are also other interpretations that work. Are you still with me? I know this is kind of dense. We're close to wrapping up this whole science discussion. This is Erwin Schrödinger. He was an Austrian physicist. And do you remember this thing that I showed you earlier? It's known as the Schrödinger equation, and it's a partial differential equation that describes how the quantum state of a quantum system changes over time. He formulated it in 1925, and it won him the 1933 Nobel Prize for Physics. In the 1930s, he was following the writing and experiments of Albert Einstein, Boris Podolsky, and Nathan Rosen. And they had some issues with the strange nature of quantum superpositions. Specifically, they had some issues with the wave function collapse proposed by the Copenhagen interpretation. They described a thought experiment, which became known as the EPR paradox after their initials. And they published a paper on it in 1935. The short version of the EPR paradox is essentially that if any particle's position is unknown until it's measured, suppose two particles interacted with one another at some point. Then, if you knew the nature of the interaction, you could measure one particle and predict the second's location or some information, some measurement about that second particle before you knew the result of the second measurement. That concept would later be called quantum entanglement. They claimed that the outcome of a measurement is known before the measurement takes place. Then, if that's possible, there must exist something in the real world, some element of reality that determines the measurement outcome. Now, Schrödinger exchanged letters with Einstein about this article. And at one point, Einstein pointed out a much easier to understand takeaway from all of this. Based on the EPR findings, an unstable keg of gunpowder will, if left after a long time, contain a superposition of both an exploded and an unexploded state. It's literally exploded and unexploded at the same time. Now, Schrödinger simplified this further with the thought experiment you probably know him for. I hope you'll forgive this illustration of Schrödinger's cat. A lot of hard names in this talk, by the way. It's not an entirely accurate illustration, but it's far less depressing than the real situation. Now, Schrödinger proposed a scenario with a cat in a locked box with a tiny bit of a radioactive substance and a Geiger counter and some kind of a mechanism that was hooked up to the Geiger counter so that if the Geiger counter detected even a single atom of radioactive decay over a period of time, it would shatter the flask of poison and kill the cat. That cat doesn't look happy. I wouldn't be either. Now, according to him, the Copenhagen interpretation implies that the cat remains both alive and dead until its state is observed, until someone opens the box. Now, Schrödinger wasn't promising that the idea of dead and alive cats was a serious possibility. He wasn't promoting that at all. He intended the example to illustrate the absurdity of the existing view of quantum mechanics. Years later, in Dublin in 1952, he gave a lecture during which he warned his audience that what he was about to say might seem lunatic. It was that when his equations, the Nobel Prize-winning equations that were described earlier, seem to be describing several different histories, they are not alternatives, but they all really happen simultaneously. And this is the earliest known reference to an alternative implementation of quantum mechanics that's been labeled now the many worlds interpretation. This idea was going to be more formalized by Hugh Everett in 1957. He called it the relative state formulation. And the claim is that it isn't just tiny particles that have a wave function of possibilities, but everything. Everett's thesis introduction read, "Since the universal validity of the state function description is asserted, one can regard the state functions themselves as fundamental entities, and one can even consider the state function of the entire universe. In this sense, this theory can be called the theory of the universal wave function, since all of physics is presumed to follow from this function alone." In an early draft of his doctoral dissertation, he explained it in a way that might make a little more sense. As an analogy, one can imagine an intelligent amoeba with a really good memory. As time progresses, the amoeba is constantly splitting, each time the resulting amoebas having the same memories as the parent. Our amoeba hence does not have a lifeline, but a life tree. And I think this excerpt from a letter Einstein wrote to Schrödinger over 15 years after they had begun correspondence about the EPR paradox is a fitting way to wrap up our crash course on quantum mechanics. Einstein never stopped being frustrated with the ad hoc nature of the wave function collapse. It felt to him like a cop-out, as it surely did to Everett, whose relative state formulation seemed to suggest that the more real thing is the state functions themselves. They're the fundamental entities from which all of physics could then follow. Reality, or truth, then, becomes a question of perspective. How much reality is enough? A while ago, I told you that estimates are lies, and I still believe that to be true. Taken individually, estimates are wildly inaccurate. We don't know how accurate our estimates are going to be in advance, and we have no way of knowing for sure how long it's going to take us until the moment we deliver the finished work. But the funny thing is, estimates tend to be wrong in ways that offset one another. Some easy things turn out to be hard, and some hard things turn out to be easy. And a pattern emerges. And you can use that pattern to start to base larger scale predictions on. So you end up with this paradoxical result that estimates can work really, really well so long as we can all agree to accept the ad hoc principle that they don't actually work at all. Or maybe it's more like Git. Maybe there's an objective notion of truth, and that truth, like the biggest Git repository you've ever seen, branches off into an infinite number of directions, and we can only see the tiny part of that truth at any one time. Is it any wonder then that serious people ask the question of whether or not we're living in a simulation? And it's not just one isolated individual either. There's like entire conferences about this stuff to talk about how we might all be simulations living in a simulated world. More importantly, if we were living in a computer simulation, wouldn't that mean that this talk and every other talk in the history of ever has really turned out to be a talk about video games after all? How many of you have seen the movie The Matrix? Okay, a lot of hands. It's one of my favorite movies. Now, for those of you who haven't, central to The Matrix's plot is the idea that most of us are living in a simulation called The Matrix, oddly enough, and our real bodies are actually hooked up to machines generating power for artificially intelligent life. A select few humans are free, and they can enter and leave the Matrix at will, fighting against the machines in the real world that is hellish by comparison to the Matrix. Now, I want to show you a short clip, but before I do, please know that I got the express permission of the organizers to do so. Cypher, the man on the left in this photo, has been free. He's been one of those free individuals for 9 years, and he's meeting with an agent of the machines. Just watch this.
Do we have a deal, Mr. Reagan?
You know, I know this steak doesn't exist. I know that when I put it in my mouth, the Matrix is telling my brain that it is juicy and delicious. After 9 years, you know what I realize? Ignorance is bliss.
Now, to be clear, the situation in the Matrix is not quite the one that was posed in the simulation hypothesis I mentioned earlier. And that's what makes it especially interesting and the reason that I showed you this clip. In the simulation hypothesis, there's not a real version of you. or depending on your perspective, the simulated version of you is the real one. What Cypher's asking for is fundamentally different. He knows the version of him that exists in the Matrix isn't the real one, and he says ignorance is bliss. He wants to make a deal that will plug him back in and make him forget that it isn't real. He wants to make the simulated reality his reality again. Which brings us back to abstractions. Okay, I think I'm ready to share my feelings about abstractions now. It's been said that science is the search for truth. How many of you have degrees in computer science? Some hands go up. Great. Do you spend a lot of time searching for truth? Looking for code examples on Stack Overflow doesn't count, by the way. You might say, well, but it's an applied science. Or, I'm a software engineer. It's an engineering discipline. And that's fair. There are very good cases for applying engineering principles to what we do. But even then, we've only expanded our definition from searching for the truth to applying truth. Now, for some reason, we shy away from labeling ourselves as artists, but I feel that we spend far more of our time being artists than being engineers or than being scientists. And there should be no shame in that. Artists move beyond searching for truth or applying truth. They express truth in their work. Sometimes they even create truth. And that's what we try to do with abstractions, even though I said earlier that abstractions are lies. Now, a good lie, and by extension a good abstraction, aids in the suspension of disbelief. It's a lie for your own good that makes it easier to believe something that will give you enjoyment or reduce your suffering. Now, when a magician pulls a rabbit out of a hat, you don't have to really believe that he has magical powers. You just have to be able to suspend your disbelief in order to enjoy the show. An important corollary to this, however, is that the suspension of disbelief causes harm. If the suspension of disbelief causes harm when broken, then it's no longer a lie for our own good. Like, for instance, let's just say you go see a magic act, and convinced that magic is real, you go home and try to saw your spouse in half. We've taken suspension of disbelief too far at that point. Now, the context in which someone perceives an abstraction influences the truth of it. For instance, if I show you this code, you don't assume that if I create a person and I give him the name Ernie Miller, that I've literally created myself, that I've literally created a person. The object represents certain dimensions, certain aspects of me. I can count on another programmer to have that shared context. So I can show this and say, this is a person. Now, earlier this year, I spoke at a conference called Ruby on Rails in Bend, Oregon. The organizers had a surprise that they gave all of the speakers. Here's mine. This is me with my cat, Esther. Now, when I said this was me, you understood that this was a portrait of me portraying an artist's perception of my physical appearance. I didn't have to tell you that. This is me, too. And again, you make the assumption that this is my physical appearance when I was younger, rocking that amazing mullet. If someone says Ernie Miller to you, and you happen to know me in person or from Twitter, this is probably how you picture me. But is it me? Well, no, it's just a photograph. But at that point, making that distinction feels a little bit silly, doesn't it? And that's because humans are hardwired to recognize other humans. We associate an image of a person with the actual person as readily as we recognize our own reflections in a mirror. It's elemental. We can build on that understanding. Now, once we believed that water, fire, earth, and wind were the elements, and that everything that existed was made from them. Now we know about atomic theory and the elements in the periodic table, and we also know that those don't exist without something even more elemental, the elementary particles. But given how useful it is on its own, and the jumping complexity between the elements and elementary particles and quantum mechanics, et cetera, remember, we still don't fully understand how particles work. The periodic table remains and will continue to remain in wide use. So how does an abstraction become elemental? Well, It does so by being pervasive, persistent, and practical. The thing about elements is they feel intuitively true. They're everywhere, and they have been for a long time. They may be made of even more elementary things, but they're also incredibly useful on their own, and even without understanding what's underneath them. They are the things that we compound together in our own creations. Well, what do they look like for a typical web application developer? I believe the periodic table of web application has 4 elements: CSS, HTML, SQL, and JavaScript. Now, when I realized this, I started to understand a little better where all my feelings about these abstractions that I was talking about earlier were coming from. So let's unpack some of these feelings. When I first started out with Rails, I was an abstraction layer junkie. I wanted DSLs, I wanted class macros, and I didn't realize it, but I basically wanted my code to look nothing at all like Ruby. It all just looked so pretty. When Haml came along, I took one look. I said, yes, please. It looks so clean, so elegant. Same thing with Sass. Look how pretty. Variables, nesting, mix-ins. Yes, yes, and yes, please, all of those things. CSS sucks. I want something better. And with CoffeeScript, well, I mean, look how beautiful this CoffeeScript is. If you squint a little bit, you can almost convince yourself it's Ruby. Before CoffeeScript was the one true way, I also tried RJS. Anyone remember RJS? Where you were writing like a Ruby template language to create little snippets of JavaScript? How about Active Record? I mean, it's obvious that being able to load a record in and make a few changes, then save it right back to the database is just way simpler than writing the SQL to do that same thing. But the thing is, Haml isn't elemental. It tries to stand in for HTML, but knowing how to write Haml doesn't prevent you from needing to know HTML. When you're testing your pages, you're still going to be looking at HTML. And Haml doesn't want anything to do with even the simplest HTML. If you try to feed Haml an HTML file, it yells very loudly at you. You're agreeing to deal with Haml's opinions about how you should structure method calls on long lines, insistence on specific indentation, and a whole lot more. If you collaborate with designers, they now need to know how to understand Haml as well. Get ready to hunt down obscure fixes for edge cases you wouldn't have needed to even think about if you were using something elemental. With Sass, there's no denying the language provides some very clear benefits over CSS, but then it takes one step too far and decides that it needs to change the parts of the language that we're working. The same problems apply once again. CSS is not valid Sass. Same story with CoffeeScript. If you don't already know JavaScript, then you're not going to have a good time trying to debug your CoffeeScript. But CoffeeScript isn't JavaScript. It's got some great feature additions, and it was especially tempting back when JavaScript was even more horrible to write than it is today. But still, you'll find yourself thinking that both JavaScript and you have to think basically in both JavaScript and CoffeeScript in order to be productive. You have to think about the JavaScript that your CoffeeScript is going to generate in order to really do well with it. The active record case is a little bit trickier because there are plenty of people who start using it before they even know SQL. And I really do love that active record reduces the barrier to entry for new programmers. But sooner or later, the pain comes. It's especially likely once domain logic gets added to the model and associations and callback chains and that type of stuff come into play. But even the simplest case can prove surprising. Here, we're loading 2 instances of the same record in the database, Ernie 1 and Ernie 2. Next, we change the first name in one to Ernest. We change the last name in another to Miller III. And then we save it. Then we check the full names of both Ernie 1 and Ernie 2. And we see that neither has data that matches what's actually in the database now in Ernie 3. Now, a complete beginner might be surprised to see that any of them are different. Someone a little further along down their learning is going to realize, well, there's no way the first record's going to know about the updates that were made to the second because that happened afterwards. But they might reasonably suspect that the last record saved would have overwritten the first, and so therefore it would match in a last one wins scenario. It would take someone with even more experience to know that this is the expected behavior in a case like this, and then someone even further along that line to explain why. Active record tracks which attributes are changed, and it only sends the ones that are changed in every query that updates the database. So each save updated 1/2 of the person record, making neither copy match the end result. Behavior before Rails 2.1 was to save the entire record, which would have been a last save win scenario like the previous example would have expected. So this is a classic example of what happens when your suspension of disbelief suddenly is broken by an abstraction. And it's jarring. It's one of those things that's like, what's going on here? And it's a really, don't get me wrong, it's a really difficult position to be in. If I'm maintaining active record, every time one of these kinds of issues comes up, I'm going to have to choose from one or possibly more of these options to make steps towards a resolution, and all of them have problems. Okay, so you could abandon database independence. It's a lie anyway. The minute you do anything interesting with your database, you're going to lose database independence. You'd go with PostgreSQL because, let's face it, it's the right choice. Then you could use Postgres' returning clause to get the updated row back and update an in-memory record every time you touch the database. Of course, there's no guarantee that won't confuse people either. It's not really a solution at this stage of the game. It leaves too many people out in the cold. And besides that, it's a moot point anyway because Basecamp uses MySQL, so it's never going to happen. You could also make a massive tweaks to the APIs. You could make changes both internally and externally, maybe backing slowly away from some of those strongly held opinions, those many opinionated decisions that were made so far, and instead exposing them as choices in the form of different classes of collaborating objects, maybe use some dependency injection, anything except for a massive chain of module inclusions. But because people have been encouraged up to this point to intertwine their domain models with their persistence models, this kind of change is sure to create a backlash in the community as people see app breakage. Even with a major version number upgrade, it's kept us back from doing a lot of these things in Active Record up to this point. Not to mention the amount of the gem ecosystem that's built around Active Record that would break overnight. Maybe you could add a configuration option. If you add a configuration option, you're possibly pleasing everyone, but you've also just added a lot of branching logic into your own code, and even more if the configuration options interact with one another in some way. Or maybe you just choose the one you think is going to work for the most people, or just for you if you're selfish like that, and you document the heck out of it. You remind them that there's always DB connection and find by SQL if they aren't happy with the choice that you made. I'm of the opinion, by the way, that well-documented does not equal discoverable, and it certainly doesn't equal intuitive. So yeah, none of these options is great. What's your alternative? Well, there are other ORMs out there, and they've chosen to make different trade-offs. Some of them are pretty darn nice, in fact, but it's a learning curve. Personally, I think we might see a big shift in our own code if we just did this one weird trick. What if you renamed your active record classes to end in record and you set their table name and started pulling your domain-specific logic out of your active record objects and into some sensible object, like we do in object-oriented programming? By isolating your more complex logic, you'll get better insight into where your pain's coming from. You might, while you're at it, consider finding a place to store your domain-specific query logic with method names that describe what they do and in what context, because it's kind of what you do in OO. So, wow, we just spent a lot of slides talking about Active Record and the web application element of SQL. So what about the other three elements? What kinds of lies would help us instead of hurt us? It's important to recognize that HTML, CSS, and JavaScript are complete languages with a deployment target. The browsers, and a ton of developers who already have experience working with them. We need these languages in front of mind where we work every day. So how do you tell helpful lies involving a concept that's so entangled with a specific language that the language itself has become elemental? You can apply the same open-closed principle that you'd apply in OO design, but at the language level. What do I mean by that? Well, for instance, eRuby got this right. A plain old HTML file is totally valid eRuby. You only trigger Ruby interpretation when you ask for it with special tags that aren't valid HTML tags. And that part's important. We're extending the language. We're not modifying it. SCSS gives you all of the good stuff that's in Sass without breaking anything that exists. You can pipe regular CSS through it. It works just fine. Just opt into the new features as you want them. And lastly, ES6, 2015, whatever the heck they're calling it this month, it's really nice, by JavaScript standards anyway. And once again, you only get those features when you opt in. So, we're wrapping up now. All abstractions may be lies, but the good ones help us suspend disbelief. They behave as though they're true. Don't miss this. The real power of abstractions lies in their ability to affect the way we perceive the world around us, which in turn frees our mind to consider new possibilities. Every single day, every line of code you write has the opportunity to create change. Or consider this perspective. If people were living in the simulated universe that you built, would they find a beautiful logic in the design that would compel them to keep looking, to keep seeking some deeper truth, a more real reality? Or would they assume it was all just random chance? Then, like the artist you are, go create the real. Thanks. I'm out of time, so if you have questions, please see me on the next break.
Yeah, I think we have some time for 1 or 2 questions. So if anybody has to ask some questions.
I
No
can't see,
questions?
so if you can see, tell me if somebody does.
Okay, so you can catch Ernie in the breaks and ask him whatever questions you want to ask.